Hi, I'm Nicole Manzanero, and in this video I will analyze the ORF10 protein sequence of the SARS-CoV-2 virus and compare it with the pangolin coronavirus sequence. My goal is to demonstrate how to calculate sequence similarity using the Blossom substitute matrix and interpret the results using statistical concepts such as an e-value. So my dataset consists of two protein sequences. The first one corresponds to the SARS-CoV-2 virus, and the second one to a pangolin coronavirus sequence. Although this is a small dataset, it allows us to apply sequence comparison methods and understand how similarity is evaluated. Now, to compare these sequences, we use the Blossom 62 matrix. This matrix assigns scores to amino acid substitutions based on evolutionary data. Positive values indicate substitutions that occur frequently, while negative values indicate rare substitutions. As I explain later, this matrix assigns a numerical score to each pair of amino acids based on how frequently they are substituted in their evolution. Here we have our both sequences. First, we input both sequences into Excel, placing each amino acid in a separate row so we can compare them position by position. And since these sequences have different lengths, we are not considering gaps. We compare only up to the shortest sequence and ignore the extra amino acid in this case. Next, for each position, we take the pair of amino acids and look up their corresponding value in the Blossom matrix. For example, comparing methionine with methionine gives a positive score. The scoring function is defined as the sum of all substitution scores across the aligned positions. In Excel, we implement this function using the sum formula, which adds all the individual scores to obtain the total alignment score. And this is the score that we get, which as you can see is 173. This high alignment score indicates strong similarity between the sequences. Based on the concepts that I discussed previously, this suggests a possible evolutionary relationship between them. To evaluate whether the similarity between our sequences is statistically significant, we use the e-value. This value represents the expected number of alignments with a score equal to or greater than the observed one that could occur by chance. Now, the S-value corresponds to the alignment score we calculated in Excel using the Blossom 62 matrix. This is the only parameter in the formula that we directly computed. The values M and N represent the length of the two sequences. In our case, these are known values, so they right now do not limit the calculation. Lambda, however, is a statistical parameter that depends on the scoring system used, such as the Blossom 62, and the background probabilities of amino acids. It determines how quickly the probability decreases as the score increases. However, lambda is not directly provided and must be estimated through statistical modeling of many random sequence alignments. Therefore, we cannot determine its exact value in this context. Now, K is another statistical constant that depends on the size of the search space and the properties of the scoring system. Like lambda, K is obtained through empirical calibration using large datasets, so it is not available for direct calculation in this analysis. As well, the e-value depends on the size of the dataset being searched. Since we are only comparing two sequences and not performing a database search, this parameter is not defined. And although we know the alignment score and the sequence length, we cannot compute the exact e-value because the parameters lambda and k, as I said previously, are not available. These values are typically estimated by tools like BLAST that use large-scale statistical models. However, we can still interpret the result qualitatively. Since our alignment score is high, the exponential term in the formula becomes very small, which results in a very low e-value. So this indicates that the similarity between the sequences is unlikely due to random chance and suggests a biological meaningful relationship. Now, to interpret whether the similarity between our sequences is meaningful, we use the framework of hypothesis testing. This allows us to distinguish between similarities that arise only by chance and those that reflect a real biological relationship. In this context, the null hypothesis states that the similarity between the two sequences is due to random chance. This means that any observed matches are not biologically meaningful, but rather occur randomly. The alternative hypothesis states that the similarity is biologically meaningful, suggesting that the sequences may share a common evolutionary origin, which is referred to as homology. Now, to evaluate this hypothesis, we rely on the alignment score we calculated using the Blossom 62 matrix. This score takes into account not only exact matches but also conservative substitution between similar amino acids. In this case, the score is high, which indicates that many positions are either identical or involve substitutions that are commonly observed in evolution. However, a high score alone is not enough to conclude that the sequences are related. We need to determine how likely it is to obtain such a score purely by chance. This is where statistical significance becomes important, because even random sequences can sometimes produce regions of apparent similarity. The e-value helps us to quantify this probability. It represents the expected number of alignments with a score equal to or greater than the observed one that could occur by chance. Because the relationship between score and probability is exponential, even a moderate increase in the alignment score can result in a large decrease in the e-value. Now, given that our alignment score is high, we expect the e-value to be very low. This means that the probability of observing this level of similarity by chance is extremely small. Therefore, we can reject the null hypothesis. As a result, we conclude that the similarity between the ORF10 sequence and the pangolin sequence is likely biologically meaningful and may indicate a homologous relationship. However, it is important to note that statistical significance does not always guarantee biological significance. There is still a possibility of error, such as false positives, where sequences appear similar by chance. Therefore, statistical analysis provides strong evidence, but it should be combined with additional biological context to make a definitive conclusion. So, in conclusion, by applying the Blossom 62 scoring system and interpreting the results using statistical concepts, we determined that the ORF10 protein and the pangolin sequences show strong similarity, suggesting a possible homologous relationship. Now, these are my references. The first one, I use it in order to know how to use the Blossom 62 matrix to get the alignment score. Then the second one, I use it to know what is the Blossom 62 matrix. And the third one, I use it to know a little bit more about the e-values and how this one is computed.